People already joined. Okay, so today we have Dr. Denis Baranov, who is kindly accepting our invitation to give a talk today. Thanks to Denis. I would like to introduce a little bit Denis now. He received his PhD degree in physics in Moscow Institute of Physics and Technology in 2016. Then he joined Timur Shagai group at Chalmers University, and they actually published quite impactful research there. They did quite impactful research there, and now he came back to Moscow, and he's now a senior researcher at the MIPT, and his research is basically focused on the moment on the counterintuitive extraordinary effects and interaction between light and matter. He's in particular, he is very interested in general aspects of scattering theory by different resonance systems, as well as the processes in perfect electromagnetic absorption and lasing, in particular behavior of coupled quantum emitter cavity systems, I guess, and today the talk will be also touching these aspects as well, and as well as the properties of the vacuum states of optical structures. And the talk title is the following. We are gonna learn a little bit about meta atoms and chiral resonances, chiral resonators for new optical vacua. So thank you very much again, and the floor is yours.
Good morning, everyone. Thank you for joining, and thank you, Anton, for your kind invitation and introduction and invitation to this nice series of seminars. I am pleased and honored to give a talk here today and to see this big audience. So before I jump into the real contents of my talk, I want to give quickly a shout out to all the people that contributed to the results that I will be presenting today. There's a lot of people from Chalmers because, like Anton said, I have worked there for years, side by side with Timur Shagai and also a bit with Mikhail Shell. And Timur gave a talk back in January in this seminar, so you're going to see some intersections with his talk, but I'll try to stay on a different side of this research line, okay? But Uwe contributed a lot to our experimental findings, and now he's an assistant professor at DTU. Benjamin made a very important contribution to the theory side of quantum system. And then I can't overestimate the impacts, the inputs of Kirill and Maxim to the chiral parts of my research that I will be showing by the end of my talk today. So now let me cut to the chase and let me give a quick intro into polaritons, which for sure don't need a lot of introduction in this audience, but I'll try to cover the basics, okay? So what we studied with Timur, what I'm studying now on my own can be summarized as study of strong interaction between light and the matter. Well, light is typically, in our cases, is represented by a discrete single optical cavity mod localized to some nanocavity, and matter is typically represented by some kind of quantum emitter, such as a two-level atom, an organic molecule, a collection of those molecules, quantum dot, and so on and so forth. And we like to, there are different ways to model strong coupling and polaritons for sure, and we've seen different ways during these seminars earlier, but we like to model these systems with different versions of the basically coupled oscillators model when we have in the low excitation limit, meaning that the two-level system is not saturated to the excited level. We can describe the system linearly in the linear approximation as two harmonic oscillators, one oscillator being the lossy cavity mode, the other oscillator being the matter excitation, which can be an electronic transition, a vibration transition, and so on and so forth. And then there is an emission coupling between the two components, okay? And you can find many reviews on this topic in the literature here. I listed just a few. The list, of course, is not complete. And we are particularly interested in the strong coupling regime of this interaction when the eigenenergies of this system, mathematically speaking, the eigenvalues of this 2x2 matrix, when they experience a splitting via the exceptional points and split into the upper branch, which is called the upper polariton, and the lower branch, which is called the lower polariton. And these two eigenstates, they carry the hybrid nature, that is, their wave function is 50% light, 50% matter, and that explains a lot of interest to this kind of states of hybrid system, okay? And typically, what people use in order to implement this kind of polaritonic states are molecular emitters. Molecules, atoms, quantum dots, semiconductor excitons, to name a few. And of course, this is a feasible and viable and very well studied platform. But these molecular emitters, let's say they have their own limitations. And the first limitation, of course, is that the dipole moment of these emitters is quite weak. And the transition dipole moment is one of the key characteristics that in particular determines the resulting coupling strength. And the coupling strength, G, is probably the most important figure of merit in this business. And molecular emitters with their dipole moments of 1, 5, maybe 10 dBi at best is really not what you can dream for. Then they also bleach, they degrade over time, especially if they are subjected to background ambient air. There are only limited ways to customize them. Of course, you can ask a next door chemist to slightly tune your molecule to shift its resonance, but these ways are limited. And as long as you are not interested in nonlinear effects, of course, these molecules have only one excited level, and you cannot go above that. So at some point with Timur, we came up with a strategy to replace these molecular emitters with plasmonic metatoms. And by plasmonic metatom, I mean simply plasmonic nanoantenna, for example, a metallic nanorod. Okay? And you could say, hold on a second, Dennis, these metatoms, they aren't quantum emitters, right? How can they show Rabi splitting and strong coupling? Well, of course, they aren't quantum emitters because they don't have just two levels, ground and excited, but they are harmonic oscillators, and they have an entire ladder of energies like any harmonic oscillator in quantum mechanics. And there are transitions between the states, okay? And these transitions between different states are characterized by a transition dipole moment, just like transition in a two-level system is characterized by the same transition dipole moment mu. And this dipole moment, when it interacts with the photonic field, it will couple, and it may show very similar effects. And unlike molecular emitters, these plasmonic metatoms offer significant upsides in comparison to molecular emitters. First of all, their dipole moment is much, much bigger than the dipole moments of molecules, order of magnitudes bigger. They're highly stable. They do not degrade over time. Well, maybe they only get covered with an oxide, very thin oxide shell, but that's really nothing. It is super easy to tune these metatoms simply by changing their geometry and therefore adjust the resonance wavelength of these metatoms to our needs. And they have harmonic energy ladder, which in some cases can be downsides, in other cases can be a positive thing. Okay, so we decided a few years ago to test this idea with Timur, and we fabricated these arrays of gold nanorods and placed them in the median plane of a Fabry-Perot cavity. So now what we have is a Fabry-Perot cavity mode sandwiched between these two gold mirrors, and we have an array of metatoms. So now we can expect that these matter atoms, their dipole moments will couple to the vacuum field of the Fabry-Perot cavity, and the resulting system should exhibit some kind of hybrid polaritonic states, despite the fact that these matter atoms are not quantum emitters, but like I argued previously, they still should couple to the photonic field and perhaps show something similar. And because of the huge dipole moment of these nanorods, and simple estimations show that the dipole moment of a nanorod of length 200 nanometers should be around 30,000 dBi, which is huge, just incomparable in contrast to 10 dBi dipole moments of a typical molecule. The resulting Rabi splitting or mode splitting should be also much larger. And to begin with, we performed numerical simulations of the field distributions induced inside the system by illuminating with a plane wave. Okay, and what we saw is that at two resonances of the couplet system, the electric field already shows pretty interesting signs of interaction. In particular, you can see that the electric field in the vertical plane of the cavity shows the opposite symmetry at the two hybrid resonances, while at the lower energy resonance, you see the opposite symmetry between the polarization of the nanorods and the electric field of the cavity away from the nanorods. At the upper energy, at the high energy resonance, you see the opposite symmetry when the dipole moment and the electric fields are aligned in the same direction. And this already suggests that these two resonances that we can see numerically, they have some kind of polaritonic nature, right? So next we modeled, we described the system using Hamiltonian approach. And because we knew that the coupling strength in the system is very large, we knew that we cannot use simply James-Cummins or even coupled oscillators model, because at some point with our coupling strength, this model would just go out of the window, it will break down. And what we needed is the full, most rigorous Hamiltonian that accounts for the interaction, not perturbatively, but to the full extent of this interaction. And the Hamiltonian that does that is the Hopfield Hamiltonian. In this case, we use the Hopfield Hamiltonian in the Coulomb gauge. So the Hopfield Hamiltonian is essentially consists of the photonic part, which is a dagger ray, the energy of the electromagnetic field, the energy of our meta atoms, and the interaction part. And the interaction part is what is really interesting in this Hamiltonian, okay? So you can see here the familiar Rabi type interaction. But besides this Rabi type interaction, you see also this exotic term, the A squared term, sometimes called the diamagnetic term, excuse me, which originates from the expansion of the light matter Hamiltonian in the minimal coupling approximation. And this Hamiltonian, of course, is not diagonal. It requires the diagonalization, which can be done analytically. I'm not going to dive into that. But an interesting feature of this Hamiltonian, and a very interesting feature of the resulting eigenstates of this Hamiltonian, is that if you calculate the vacuum energy of the couplet system, and the couplet system basically is two new polaritons. It's the lower polariton and the upper polariton. And these two polaritons are new harmonic oscillators in its own right, okay? And we know from the textbook what the vacuum energy of a harmonic oscillator is, right? It is just h bar omega over 2. So here in the couplet system, we have two polaritons, and the vacuum energy of the couplet system is this. It is h omega plus h bar omega minus, where plus and minus are eigenenergies of the upper and lower polariton. And if you start modifying the coupling strength, you will see that the vacuum energy does not remain constant, okay? Quite the opposite, it shifts with the ground state. So if somehow you are able to tweak this little knob in your system, if you're able to tune the coupling strength, in real time, by doing that, you will change continuously the vacuum energy. So it will cost you some energy to change the coupling strength in the system. Even without, in the absence of any photons and excitations, in the complete darkness, it will cost you some energy to change the coupling strength because of that, okay? And in order to see how we really changing the vacuum energy, we of course measured, we performed simple spectroscopic measurements of the coupled system. We measured reflection, transmission, and analyzed the results in systems using Hopfield-Hamiltonian. So the dots here are resonant energies of the coupled system measured in experiments, and lines are fits from the Hopfield-Hamiltonian. And by fitting the dots to the theory, we saw that the coupling strength in the system attains really, really large values. The normalized coupling strength, the ratio between G and the resonant photonic energy, exceeds 0.5. It exceeds 50%, indicating that our system is well in the ultra-strong coupling regime, where we cannot neglect this diamagnetic term any longer, okay? But like I said, what is really interesting for us, what was intriguing for us, is this modification of the vacuum energy. Can we directly, or at least indirectly, observe it in our system? And we have all the data that is necessary to make this conclusion. So we take these values from the experiment and we compare. Okay, we compare the vacuum.
Sorry for interrupting you. Would you prefer questions during the talk or
after? Yes, sorry, I forgot to mention during the talk. If these are short questions, I will be happy to get interrupted and answer the questions. Absolutely. But
okay, then I have a quick short question. If you go slide back.
Yeah, go ahead.
Here, what prevents you to have experimental dots at the negative detuning?
Can you repeat, please?
Yeah. The question is, I see experimental dots on the positive side of the detuning between the cavity mode and plasmon frequency, but on the negative side there is nothing.
Yeah, that's a good question. Give me a second. I'll try to think why. I guess because the cavity energy in this experiment was controlled by the cavity thickness. So typically, when we want to make a plot like this, what one would do is change the incidence angle, right? Kx, and measure dispersion. In this particular case, we weren't able to vary the incidence angle purely for spectroscopic reasons. So instead, we varied the cavity energy by changing the thickness, okay? And for some reason, we simply were not able to push the cavity energy to this side of the detuning. That was the only reason. It is entirely possible to have such a system, and I'm sure the dots would align with the curves, but we did not fabricate the systems with the thickness that would give us dots on this side. Okay, so this was just not very, we did not look forward to having the dots here at the time when we were fabricating the cavities. Okay. I would of course prefer to have some dots here, but you can't always get what you want. So now back to the vacuum energy. Like I said, we can calculate the vacuum energy of the system simply by adding the two together. And in the uncoupled case, we have the two oscillators. We have the cavity, we have the emitter atoms. So the vacuum energy of each is h bar omega over 2. And in the coupled case, we have the two polaritons. And again, we do the same, and we subtract one from another. And this is what we saw. Again, the dots are the experimental results obtained using the measured reflection and transmission spectra and the extracted resonant energies. So what we see is that, so essentially, we managed to indirectly, using simple spectroscopic measurements, observe modification of the vacuum energy in two coupled oscillators, and the relative modification of the vacuum energy is quite substantial. It's 50% of the unmodified bare energy, which is quite a lot, in my opinion. So by coupling these plasmonic nanorods to the vacuum, you modify the vacuum energy, not by tiny amounts, but by 50%, which is quite a lot if you think about that this is not just excited state, it is the real vacuum state that gets modified, the real quantum mechanical ground state that gets modified in this system. And if you translate those 50% into absolute values, then you'll see that it is more than kBT at room temperature. So this system opens very interesting opportunities for experiments involving modification of the vacuum energy at room temperature, because all of that was done at room temperature on an ordinary optical table without any cryogenic temperatures and without magnetic fields. Just at ambient conditions, you can modify your vacuum energy in an ultra-strongly coupled system. Okay. So this we can utilize the strategy of meta-atoms in order to do something different. We recall that if you have a cavity and we fill the cavity entirely with molecules, for example, then the Rabi splitting and the coupling strength in this system is essentially limited by the saturation limit, by the bulk coupling strength, which is known since Hopfield's work. It is also called Hopfield's G sometimes. And a particular feature of this limiting, of this ultimate limit, is that it is not dependent on the cavity properties. It is only determined by the molecular dipole moment and the density of molecules. The cavity properties, the cavity characteristics simply do not determine this ultimate Rabi splitting, this ultimate coupling strength. And there are cases, there are instances when one would like to boost this coupling strength. For example, the chemistry that is studied by Thomas Edison and his team, when they demonstrated that by coupling certain organic molecules to cavities, one can substantially modify the chemical kinetics of those reactions. By strongly coupling transitions of these molecules to the cavity mode, one can modify chemistry, one can boost chemistry or decelerate certain reactions or change the balance between two different products, or change the balance, the equilibrium between the product, the reactant, and the product. And so it is interesting if we can boost the pure molecular coupling strength by using somehow our idea of meta-atoms. And in order to test that hypothesis, what we did is that we mixed our molecules, our organic molecules, with meta-atoms, and we placed that into a cavity. So now we have a polariton that consists of three components. It consists not only of the cavity and molecular emitters, but there are also plasmons which sort of mimic molecules, okay? So we tune these plasmons. Remember, I said in the beginning that we can easily customize these meta-atoms to our needs. So we tune the dimensions of these meta-atoms so that they look like molecules. They have identical resonance wavelengths as our molecules. And we mix these meta-atoms with molecules. But because the plasmonic meta-atoms, has much higher dipole moments, we were hoping to increase the resulting effective or collective coupling strength of these hybrid three components polaritons by mixing huge plasmonic meta-atoms in this mixture. Okay, and this is what we did with Carl Borison from chemistry department at Göteborg University, and this is the essence of our results. So when we have pure nanorods in the cavity, we see Rabi splitting between many Fabry-Perot cavity modes, because our Fabry-Perot cavity was pretty thick, so there's a lot of resonances. And when we insert a plasmon, and the x-axis on this plot shows you different lengths of the nanorods. So it gives basically different plasmons. And this plasmon experiences anti-crossing with Fabry-Perot cavities. And then we studied the mixture, the three-component mixture of cavity, molecules, and plasmonic meta-atoms. And we have some other dispersions. So now, using the Hopfield Hamiltonian, we can analyze the dispersion, and we can extract the coupling strength, the collective coupling strength. And this is what we saw. So, for example, having pure hexanol in the Fabry-Perot cavity, we have the coupling strength of about 40 inverse centimeters. But when we mix these hexanol molecules with plasmonic metatoms, we boost the coupling strength 5 times compared to pure hexanol, okay? Of course, this is not just the hexanol coupling strength, it's the effective coupling strength of the entire mixture. So metatoms take a lot of the coupling strength onto themselves, okay? But we hope that this platform can be useful in the scenarios when the Rabi splitting, when the coupling strength between the chemical components and the optical components is important in determining the chemistry. Our idea here, our goal was not to really test the chemistry. We did not have all the everything at our hands to test this idea, but our idea was to test the optical part of these hypotheses to see if we really can increase the coupling strength beyond the molecular limits. And these simple optical results show that it is indeed possible, and it is possible by quite a lot. So this gives us hope that plasmonic metatoms can be useful in this regard as well. And at some point, I became interested in the following question. So we saw that Rabi splitting of these systems incorporating plasmonic metatoms can be quite high. But how high exactly? What is the ultimate limit of these coupling strength between photonic fields and plasmonic metatoms? So we decided with my students to look deeply into this issue, and we consider the most primitive, the most simple system that one could consider. We considered simply a lattice, a face-centered cubic lattice of plasmonic metatoms that couples to an extended, infinitely propagating photon in free space. And we calculated the coupling strength between these periodic arrangements of metatoms and the photonic field. And we saw something quite intriguing, quite exciting. We saw that the normalized coupling strength in this system, and by the way, the system is quite universal. It does not, the characteristics, the coupling characteristics on the system essentially do not depend on the properties of the metal, because everything in the system can be normalized with the plasma frequency of the metal, and the results can be presented in the model independent way, and can be presented as functions of the completely dimensionless size of these metatoms, the radius normalized by the plasma wavelength of the metal, and then all the data obtained for all the different plasma frequencies basically follows the same universal behavior. And what is interesting, what is intriguing about this behavior is that, first of all, very quickly it goes into the ultra-strong coupling regime, then it goes into deep strong coupling regime when the normalized coupling strength exceeds 1. This is even more exotic regime than the ultra-strong coupling. And it looks like this normalized coupling strength approaches a universal constant. You see it asymptotically approaches some number which is around 1.2 or something. And you cannot go above this value with spherical metatoms. Probably you can go above with spheroidal metatoms. We are looking at spheroidal structures right now, but spherical metatoms simply do not allow you to go above. So there is a universal constant, okay, determined, imposed by the system, above which you simply cannot go. And this is pretty interesting. It is interesting what exactly determines this and whether it is possible to express this universal constant in terms of some fundamental constants, maybe fine structure constant and something else, because there is nothing else. And maybe the geometry, right? Because there is nothing else that could determine this limit.
Denis, may I ask a question?
Sure.
Quick question. How does, just curious, how does the period of the lattice affect the result? Okay, we learned how does the radius, but the period.
Yeah, of course, we studied this problem in the limits of densely packed spheres when the filling factor is 0.74, famous textbook problem solved by Gauss a few centuries ago. But if you now spread, if you start increasing the distance between the particles, of course, that will reduce the coupling strength because you have less atoms, less matter atoms per unit volume, okay? So you have less density and you have less coupling. Makes perfect sense. And in the case of completely diluted array, the coupling strength will vanish as the square root of density. Okay, so now let me switch gears and talk about something different. Let me speak about chirality, my favorite parts of this story. So seeing those results with matter atoms, with simply flat, homogeneous, straight matter atoms, we got curious at some point. Can we now couple chiral matter atoms strongly to cavities? What happens if we use some chiral atoms or chiral matter atoms and we place them into cavity field and couple strongly? Specifically, we were curious whether it is possible to imprint the vacuum Rabi splitting, not only in transmission and scattering, which is what is usually measured in spectroscopy of strongly coupled system, but whether it is possible to imprint Rabi splitting on circular dichroism. Circular dichroism is a hallmark of chiral system. I will explain what it means later. And we were curious whether it is possible or not. Because if it is possible, it opens up a lot of interesting opportunities for chiral sensing. As many of you know, chiral molecules are pain in the ass to measure and characterize because their chiral resonances are typically somewhere in the UV range, and measuring molecular systems in the UV is always challenging because we don't have a lot of reliable sources and detectors, and it is very expensive to measure in those regions. So if we could induce Rabi splitting between the cavity and the chiral molecule, and if we could downshift one of the chiral peak to lower energies down to the visible range, that would be very cool. That would simplify sensing of chiral structures. And that was our motivation to study coupling between photonic fields and chiral matter atoms. But before I go any further, I want to cover the basics of chirality in electromagnetism. Okay? So we say that an object, a geometrical body, is chiral if a mirror image of that object cannot be superimposed with the original object by a series of rotations and translations in the Cartesian space. And the best example is the pair of our hands. No matter how we move them, how we rotate them, we will never merge the two in space. Okay, our palms are perfect examples of geometrically chiral objects. So to make any object chiral, we need to break any mirror and inversion symmetry. That yields a geometrically chiral structure. And geometrical chirality has far-reaching implications for the electromagnetic response of structures and media. Particularly, geometrical chirality of a continuous medium induces magnetoelectric coupling, meaning that there is now a relationship between the D field and the H field, and the B field starts to depend on E. So this magnetoelectric coupling response mixes all the fields, all the four fields in Maxwell's equations. And in the most simple case of bi-isotropic media, such as, well, I guess sugar would be an example of bi-isotropic media, the strength of chirality is characterized by the Pasteur parameter, kappa. So turns out, not only geometrical bodies can be chiral, but the electromagnetic field as well can be chiral too. And loosely speaking, chirality of electromagnetic field is related to the circular polarization of propagating plane waves. Okay, we know that plane waves can be right-handed, left-handed, And this gives you a sense of twist, this gives you a sense of chirality or handedness of fields. But rigorously speaking, chirality can be characterized by the following pseudo-scalar quantity C, which is called the chirality density. And loosely speaking, it characterizes the sense of twist, local sense of twist in electromagnetic fields. And now, if we merge the two together, if we merge the chirality of matter and the chirality of light, we will get the result is the famous effect of circular dichroism, which underlies numerous, endless ways to characterize chiral molecules. And I don't need to say how important chiral molecules are in our lives, in fundamental science, as well as in life sciences, because many biomolecules are chiral, our DNA is chiral, many drugs are chiral, with the famous example of ibuprofen, when one of the two enantiomers, and enantiomers are two mirror images of the same molecule. And in the case of enantiomer, in the case of ibuprofen, one of the enantiomers is 100 times more potent than the other one. So the other one is virtually useless. So it's very, very important to be able to discriminate and separate the two enantiomers physically in space. This is why being able to study chiral systems, chiral molecules, and the interaction between chiral fields and chiral matter is super important for science, for fundamental and life sciences. So back to our idea of testing whether it is possible or not to imprint Rabi splitting on circular dichroism. Of course, we tested this idea using our concept of metatoms, but this time we fabricated chiral metatoms, these bananas or crescents, if you like, which are truly geometrically chiral because they lack any mirror and inversion symmetry. And we place these chiral metatoms in a Fabry-Perot cavity formed by two gold mirrors, as always. And we saw exactly, at first we saw exactly what we were hoping to see. We saw that not only unpolarized transmission experiences Rabi splitting, just like it should, but also circular dichroism, which was measured as the differential transmission rate, also experiences Rabi splitting. So while bare metatoms show Rabi splitting at this wavelength, show peak NCD at this wavelength, the couplet system of cavity plus metatoms shows Rabi splitting in circular dichroism, and while one of the peak goes to high energies, the other peak goes to low energies. And we were quite excited at first. This is what was exactly what we wanted to see. But then we started to look deeper in these spectra, excuse me, and we modeled analytically some simple systems incorporating just a homogeneous chiral biisotropic field in the cavity. And we saw something that worried us a lot. We saw something that made us question these results. So we placed a homogeneous biisotropic field between two gold mirrors, and we calculated CD, circular dichroism. And what we saw is that while circular dichroism of the strongly coupled system always feature the desired Rabi splitting in CD, no matter what we do, no matter how hard we try, the magnitude of the CD, okay, always remains below the free space CD. That is CD from the same field in free space without any cavity, without any coupling, without any resonances. So no matter how hard you try, no matter if you split your CD, no matter how strongly you split circular dichroism, the magnitude of this CD is always smaller than just the same naked film in free space. And that was a very disappointing conclusion that made us question our understanding of coupling in the system. We did not understand at that point what was going on, because this happens despite all the resonances and all the enhanced electromagnetic fields in the cavity. So the field, the intensity is enhanced inside the cavity by a lot, but this does not lead to enhancement of CD. So why? What is going on here? And we were asking these questions until we realized something very fundamental about Fabry-Perot cavities that we use everywhere in the strong coupling business. So let's see how an ordinary mirror reflects light. Let's forget about the cavity. Let's look at a single mirror. So if we have an isotropic homogeneous mirror, such as a homogeneous metallic field, or maybe a DBR mirror, then what happens when we illuminate this mirror with a circular polarized light is that right-handed light upon reflection becomes left-handed. You see where I'm going with this? So the standing wave that is then formed inside the cavity that starts to circulate between the two ends of the cavity absolutely loses any sense of handedness. It is becoming chiral, non-chiral at all. This is the root of all the problems that we faced in our previous experiment. So this is kind of what happens when we look at reflections of our hands in the mirror. Our right hand, our right palm becomes left palm, and our left palm becomes our right palm. Of course, this is not the exact mechanism, right? This is just a lousy metaphor that just remotely illustrates the point, but you get the point, right? Upon normal incidence, right-handed wave becomes left-handed, and then this standing wave flips its handedness every time it reflects from the bottom and top mirror. And the resulting resonant mode that circulates inside the cavity becomes completely achiral. This is why we cannot increase the circular diachroism in a chiral film by strong coupling. We can induce strong coupling, we can induce Rabi splitting, but because of this property, because of this unfortunate property, we cannot increase the magnitude of CD. Okay, and this is a problem that I wanted to address. And so what we want to do is we want to engineer a very tricky cavity that would support a true right-handed standing wave, so that a right-handed wave upon reflection from the bottom mirror would preserve its handedness. So the right-handed wave would reflect into another right-handed, and then it would reflect back from the top mirror again and again and again and again. And so a right-handed wave would emerge in the space between these two mirrors, okay? Which is not possible with ordinary metallic mirrors. So we need to find a way around this challenge. But I also want to impose an additional requirement, okay? I want to make our life even more complicated. And what I want to do besides that is that I want my cavity be completely transparent for the opposite handedness. So I want to have a cavity that does support, that does trap right-handed wave, but does not trap light-handed wave at the same time, so that both mirrors are completely transparent for left-handed radiation at the same wavelength. Okay, and now why I want that? Well, because now if I place a right-handed molecule in the cavity, that right-handed molecule would couple to the right-handed standing wave, right? And maybe it will couple strongly, and it would lead to the emergence of truly chiral polaritons. But when I place a left-handed molecule in the same cavity, it wouldn't strongly couple to anything, because there is nothing it can couple to, because there is no left-handed cavity mode, right? This is what I want to do. So the question is, can I design such an unusual optical cavity with such a strikingly different behavior for two polarizations? Turns out we can, but it is a tricky business, because you see, if we want to preserve the handedness of light upon reflection at normal incidence, that means that the reflected wave, the electric fields in the reflected wave must circulate in the opposite direction, because the handedness mathematically speaking, handedness is the projection of spin on the propagation direction. And the spin of a plane wave basically tells you which way the electric field rotates. So if my incident wave rotates like this, the circular polarization rotates this way, then my reflected wave needs to rotate in the opposite direction. And this is difficult to do. This is really difficult to make a circular polarized wave rotate in exact opposite direction upon reflection. But there is a way to do that. And in order to attain this behavior, we need to break a lot of symmetries. And this sketch shows an example of the system that allows attaining the desired polarization behavior. So first and foremost, we need to break any vertical mirror symmetry in order to enable different behavior of right-handed and left-handed incident waves. Because remember, what I want to do is that right-handed wave is reflected and left-handed wave is transmitted. So I need to break any vertical mirror symmetry, and this unit cell does exactly that. But besides that, I also want to preserve my right-handed light in reflection. And to do that, I need to violate the threefold rotational symmetry around the z-axis. Because if I have at least threefold rotational symmetry, then my spin will be preserved. And if spin is preserved, this means that handedness is flipped. And this is exactly what I want to avoid. So I need to break a lot of symmetries, and this structure does exactly that. And by proper engineering and optimizing the geometry of these holes, we can obtain the desired behavior. So this is not an original design, but it was inspired by this lovely, incredible experimental paper from the Canadian team of authors, published a couple of years back. But they studied only single mirror, okay? And remember that we want to make a cavity. So this is how a single mirror behaves. It reflects right-handed light into right-handed with near unity efficiency. Reflection power, reflection coefficient was around 9.95, if I remember correctly. Whereas left-handed light is transmitted, again, with near unity efficiency. It is transmitted into right-handed, so it is very tricky, but it actually doesn't matter what it is transmitted to. We don't care about that. The important point is that it is transmitted and it does not stay in the cavity between the mirrors. It is transmitted, it is gone forever, it does not come back, but right-handed lights will circulate. So now we finally can make a cavity out of these two mirrors. In principle, we have all the necessary joint coefficients from the simulations from the previous slides, and we can stack two such mirrors together so that a right-handed wave will circulate back and forth between the two mirrors. And we can apply the transfer matrix method. We can, for a second, we can forget about all the microscopic structure of the mirrors, and we can apply the transfer matrix method. And in order for the right-handed wave to circulate back and forth, I want to emphasize that the top mirror needs to be inverted with respect to the bottom mirror. You will see what I mean by that on the next slide. So this is what happens if we illuminate this cavity with two different polarizations, with left-handed and right-handed. And you see strikingly different field enhancement behavior in the vicinity of the resonant wavelength, while left-handed incident polarization induces very strong field enhancement. For the right-handed, the cavity is nearly transparent. There is even an anti-resonance. The light just passing through the system just like we wanted. But not only that, remember that we wanted a chiral standard wave to form in the mirror, in the space between the mirror. So let's check if the chirality density is also enhanced. And it is. Chirality density for the same left-handed excitation is enhanced by a lot at resonance, whereas for the opposite excitation, it does not show any enhancement. So now we can do the same, but using full wave simulations of the mirror. We bring back the exact microscopic structure of the mirrors, because in the end of the day, they are meta surfaces. So we need to remember that they have some arrays, arrangement of holes. which was not accounted for in this calculation, because here we treat these mirrors as homogeneous things. Now we simulate numerically the structure, and this is what I mean by inversion, because the traveling right-handed wave sees each mirror from a different side. The top mirror needs to be an inversion of the bottom mirror. You see how they are inverted in comparison to each other? And this arrangement of the two mirrors, by the way, makes the entire structure geometrically chiral. If you look closely, carefully, you'll see that it lacks any inversion and mirror symmetry. Therefore, the structure is geometrically and optically chiral. And this is the field enhancement spectra as we vary the thickness of the cavity, and we reproduce exactly the behavior we saw from the transfer matrix. At some thickness of the cavity, light-handed excitation produces strong field enhancement inside the cavity, whereas for the right-handed excitation, it is nearly transparent. So far, so good. Let's check what happens with chirality density inside. So this is the field distribution. This is the spatial distribution of the electric field intensity at resonance for left-handed excitation, which produces resonant standing wave between the two mirrors. What is interesting about that is the nearly uniform intensity distribution, which is in strike contrast to the alternating peaks and troughs of an ordinary standing wave, which alternates between nodes and antinodes. You see nearly black regions here, right? But this is not so for our right-handed wave, which does not have any black spots here. And this is exactly what Zhelodov and colleagues back in 2016 called, if I remember correctly, polarization standing wave. So this is a superposition of two counter-propagating waves with opposite spin. But opposite spin and opposite propagation means they have the same handedness, right? So this is exactly a chiral standing wave that we wanted to excite, that we are exciting in this system. And it was described by Zhelodov back in 2016, the structure of this wave. And polarization, electric field polarization of this wave has a very interesting property. The intensity is nearly uniform. This is exactly what we see here. This is nearly uniform because maybe we did not match the resonant frequency exactly, but ideally it should be uniform. And electric field has linear polarization at every point of this right-handed wave, not circular, but linear. So a question that arises, of course, is whether this property of the cavity remains stable against variation of the incidence angle. And we examined what it does when we vary the incidence angle. So we varied incidence angle in the range from -5 to 5 degrees. And of course, the cavity mode experiences spectral shift, simple parabolic spectral shifts. It is negative because I have wavelength on my y-axis, but that is expected in any Fabry-Perot cavity parabolic dispersion of the modes. But what is surprising and what gave us a lot of hope is that the chiral nature, the single-handed nature of the mode actually maintains as we vary angle. So in this plot, what I'm showing this plot is the volume average chirality density inside my single-handed cavity. So I calculate chirality density at every point. I integrate it over volume and normalize it with chirality density of my incident wave. And first of all, you can see that for left-handed incidence, which excites right-handed standing wave, chirality density is enhanced by 2 orders of magnitude, and it remains negative. And negative chirality means right-handed wave. And it remains true for other incidence angles. So this property of the cavity mode, of the single-handed cavity mode, is stable against minor variations of the incidence angle, which is a very nice property. And not only that, but when we excite the same system with right-handed light, nearly the same thing happens. Of course, the enhancement magnitude is much lower, because we barely excite the same cavity mode. But the chirality density remains negative, which means that we do not excite any left-handed mode. The left-handed mode is not present in the system. This is exactly what we wanted to achieve. We designed a system that has only right-handed standing wave traveling back and forth and lacks any left-handed excitation. Okay? And now, finally, because we are always thinking about polaritons, we wanted to check how point dipoles, how point emitters modeling some quantum emitters couple to this cavity. And as you all know, when we have a single electric point dipole, we can easily calculate the emission rate of this dipole using the Green's tensor formalism. And the resulting expression, the resulting emission rate in the case of pure electric dipole emitter is dependent on the transition dipole moments and the electric density of states, local density of states, which is the property of the system. But we have something different. What we did in this test is that we placed a chiral point dipole. And what a chiral point dipole is a combination, a linear combination of two dipoles, an electric dipole and a magnetic dipole that are parallel or anti-parallel with a plus minus pi over 2 phase shift. And these two signs, plus and minus, these two combinations determine right-handed chiral dipole and left-handed chiral dipole. And because we know that there is only right-handed mode that exists in the cavity, we could expect that right-handed dipole would couple strongly to the cavity, but not the left-handed one. And this is exactly what we saw in numerical simulations. We simulated the Purcell factor of the two dipoles, of the two chiral dipoles, and we saw huge asymmetry. We saw few orders of magnitude asymmetry in the Purcell factor between the right-handed emitter and the left-handed emitter. And then we did a little bit of math, and we calculated, we expressed mathematically the emission rate of a chiral dipole. We tried to obtain an expression similar to this textbook example that all of you are familiar with. So in the case of a chiral dipole, the situation is a bit more complicated because we have electric dipole and magnetic dipole, but the structure is simple. The electric dipole does work on the electric fields, and magnetic dipole does work on the magnetic fields. And then we expand this expression using the Green's tensor formalism, and we obtain something quite interesting. We see that the resulting expression can be expanded into three contributions: the pure electric emission rate, which is essentially exactly this guy; the pure magnetic emission rate, which is the same but expressed as magnetic transition dipole moment multiplied by the magnetic density of states, plus this interesting guy, which can be associated with some kind of chirality, vacuum chirality of the field, because we know that the emission rate, speaking quantum mechanically, is determined by the fluctuating vacuum fields. The stronger the fluctuations of the vacuum field, the stronger the interaction of the emitter with this fluctuating field, the stronger the emission rate. And because this guy gives us the asymmetry, determines the asymmetry, this Xi here can be +1 or -1 for right-handed and left-handed chiral dipole. This gives us the asymmetry, exactly this asymmetry that we saw in simulations, in numerical modeling. And this made us believe that this little term, this tricky term, can be associated with chirality, chirality density of vacuum fluctuations of the optical cavity. And we can make quite a speculative conclusion at this point that the vacuum fluctuations in the cavity formed by these two helicity preserving mirrors, not only electric and magnetic fields fluctuate separately in this region, but also vacuum fluctuations acquire some chiral character in this structure that is manifested as a huge asymmetry between the two Purcell factors. And this brings me to the end of my talk. And to conclude, I want to give just a few points that would summarize my presentation. So MET atoms offer us a very interesting platform for realizing harmonic and highly tunable polaritonic states and reaching ultra-strong coupling on an optical table at ambient conditions, and using handedness preserving mirrors, we can fabricate and we can engineer unique single-handed asymmetric optical cavities that open up a lot of interesting opportunities for studying chirality of optical fields and for study of chiral polaritons and chiral optical vacua. With that, I would like to conclude and thank you all for your attention. Thank you.
Thank you, Denis, for a really nice talk. Lots of new things for me, at least I learned during your talk. Very nice, cool. So we have a couple of questions, and the first question from Helgi Sigurdsson from Southampton.
No, Anton, I was clapping.
Right. Sorry.
Sorry, but maybe a question later.
All right. Please go ahead.
I have a question. Oh, Tamsina, I think, has a question first. I also have a question.
You can go first, Pavlos, if you like. Okay. I was wondering on these, thank you for the talk, but I was wondering on these chiral preserving cavities, what happens when you excite with linear light?
Oh, so yeah, thank you. Very nice question. Well, I think you can answer the question yourself. Tell me, what is a linearly polarized light in terms of circular polarized?
It is the sum of left and right circular waves.
So it's half left, half right. So as you can see, right-handed basically doesn't do anything because the chirality amplitude is very low. It's basically transparent. So you'll have 50% excitation you have 50% of this with linearly polarized light, plus and just a tiny bits of this.
Okay, so the right-handed section would not be detrimental to the effect. It would just be transparent and go through.
Yeah. The cavity is almost transparent for this.
Okay, and the other question I had is, if you on your beam put in a Laguerre Gaussian that had this kind of phase winding within it, how would this react to the
in this case, in the case of single-handed cavities?
Yes.
A Gaussian beam with an angular momentum, right? Wow. Yeah. Well, so let me think. What is a Gaussian beam? It is a superposition in the paraxial approximation of different plane waves with slightly different propagation direction. With different polarization states. So because we are working in the, let's say we are staying in the paraxial approximation, so the incidence angle is probably plus minus few degrees, right? So I would say that this behavior will remain, as we would excite single-handed, we would excite right-handed standing wave even with a Gaussian beam. I don't know how the phase singularity, what it would do upon transmission to the cavity. That's an interesting question, what would happen with the phase singularity and with angular momenta. But simply because this field is just a superposition of differently polarized plane waves with a very small axial angle between the z-axis and the propagation direction, I would say that we would excite the right-handed wave inside, probably with some interesting spatial dependence in the XY plane. Okay?
Yeah, thank you.
It will be very interesting to see what happens in the XY plane.
Yeah, thank you.
Okay, Paulus has a question.
Yes, thank you for this very, very nice talk. So just to follow up from Tamsin's question, you know, exploiting the chirality of light is you're playing with the polarization, which is one of the degrees of freedom that you have, but really enabling these Laguerre-Gaussian modes, so really twisted light, of which you can control the polarization as well on top of that, gives you an extra degree of freedom. So I think it would be very interesting to see how this can be extended in this kind of cavities that you have.
Yeah.
Because you have the possibility to imprint this kind of dislocations that would allow one type of charge of this kind of modes to be only one type of these charges to be allowed inside your cavity in the same way that you allow for only one type of circular polarization.
Would be an interesting avenue to explore, but one has to be very cautious here, because there is a danger to start confusing the two things, the chirality and the angular momentum, because they're quite different. Like I said, there is a very intricate relationship between the spin on the one hand and the handedness on the other hand. And there's a lot of confusion in the literature between the two. And although these two properties are related on the deep level, they, at the same time, they are exact opposite of each other in some way. Because these two waves, for example, in my example, traveling in the opposite directions, they have the same handedness, but they have the opposite spin. And in these Laguerre-Gauss beams with topological phase singularities, what you have is the angular orbital momentum. So this is the spin angular momentum, SAM. Angular orbital momentum is quite a similar characteristic, but whereas spin is related to the polarization, angular orbital momentum is related to the global phase distribution of your field, right? So in many respects, I think, I'm not an expert in angular momentum by all means, but from my poor math perspective, angular momentum in many respects would be quite similar to spin. And so having a field with a defined angular momentum would not give you a definite, well-defined handedness. So by imposing a defined handedness, you sort of need to sacrifice for the orbital momentum. Does it make sense?
Yes.
What I'm
I
saying?
have a follow-up question on this, which is really on the birefringence of the media that you put in this kind of cavities.
Birefringence.
Mm-hmm. So when you engineer your cavity and you put inside your molecules, are these molecules also birefringent or not?
So right now we are not placing any molecules. So far we only tested the behavior of these cavities with point dipoles. So this is not a medium, this is a source in terms of Maxwell's equations. This is just electric current density. You're absolutely right. This is our next step. We are going to place a medium, a polarizable medium. For example, we are going to fill the space with chiral molecules. But chiral molecules are not birefringent, they are bi-isotropic. I think perhaps you meant bi-isotropic. This is a medium with a Pasteur parameter.
Mm-hmm.
This is a medium with Pasteur parameter. And when we do that, we are expected to see very interesting behavior. So if we fill the space with bi-isotropic medium, for example, with sugar or with DNA molecules or with ibuprofen, okay? And because this space between the two mirrors only supports right-handed wave, I'm expecting to see that, let's say, right-handed ibuprofen will couple strongly and show two polaritons, okay? But left-handed ibuprofen is not going to show any polaritons because it is left-handed and there is nothing it can couple to. Loosely speaking, this is the behavior that I'm expecting to see, but this has to be the subject of further work.
Yes.
This is only fantasies.
My only thought here is that any asymmetric molecule, beyond its chirality, it also carries some birefringence, if you like, yes? So just by the imagine of it like a liquid crystal molecule, yes? So any asymmetric molecule is birefringent because, of course, even if you have the same medium, the fact that it is comparable with, it is smaller than the wavelength of light, the light sees a different amount of material of a given refractive index in one direction and the other direction. And when you put birefringence inside the cavity, then practically you are mixing, you're coupling the two circular components, giving rise to the Rabi-Dresselhaus phenomena in optical cavities, as it was shown in liquid crystal microcavities.
Right. Okay. I think I know what you mean. Now I understand your point. I think this is reminiscent of what we saw here with these very, very tricky, very twisted structures. Would you call them birefringents, these metaatoms?
Just by looking at it, maybe there is some birefringence in your system.
Yeah.
How cylindrically symmetric they are. Maybe a
exactly, yeah. And this middle peak in CD, we associated this middle peak not to chirality, but to this exact degree of freedom, which some people also call elliptical dichroism. And it is very painful sometimes to distinguish between the two, between true circular dichroism, which is determined as inequality of these two Jones coefficients, right? Chirality is equivalent to this inequality. And elliptical dichroism, which can originate, for example, from birefringence. You can have an absolutely achiral system, for example, with mirror symmetry, but still you would see different asymmetric transmission rates, power transmission rates for left-handed, right-handed excitation. Yeah, this could be a very long discussion. I think I know what you mean, and I would agree with you that there is a danger to take observed apparent chiral behavior for chirality, whereas in reality it's not, and in reality it could be some birefringence of our very twisted metaatoms or molecules. Yeah, there is such a danger. So one should be very cautious with distinguishing between chirality on the one hand and other dichroic effects on the other hand.
Okay, perfect. Next is Sergey, please go ahead.
Denis, thank you very much for your talk. My question is about your first part. I think it was slide number 8 or 9, where you show the data for mixture of nanorods with molecules. So this G factor which you obtained was limited by something, and you somehow designed this structure with specific spacing and so on. So when you put the nanorods in some arrangement, yeah, how did you optimize the design of this in order to boost this Rabi, except just taking into account this square root of density?
The only thing that we need to design is that we need to match the plasmonic energy, the plasmon resonance, to the molecular resonance, so that they look sort of indistinguishable in the mixture. That's all, and that is achieved by varying, for example, the longer axis of this nanorod. This is done easily, and then you mix the two, and you don't care about anything. You take any cavity, and you are allowed to have any cavity thickness, whichever you like, and you fill the space with nanorods. For example, you deposit nanorods, you make them by lithography, then you fill the remaining space with molecules, and you have this mixture. This mixture is not homogeneous, of course. This was only the first primitive test, but it served our purpose, our idea of showing that the collective coupling strength in mixture does go beyond the coupling limits, the molecular coupling limits. And the molecular coupling limits is not dependent on the cavity too. It is only dependent on the molecule's property, dipole moments of the molecule and square root of the molecular density. So what you optimize, what you need to care for is that you need to make sure that your plasmonic metaatoms have the same resonant energy as your molecules. Because if they don't, okay, if they don't, then they are distinguishable. And they don't look like fake molecules. They look like some completely different. They don't mix together with molecules. They don't blend in, okay? So the only thing you need to worry about is really matching the plasmonic resonance to the molecular absorption bands. And then with some approximation, with some wishful thinking, you can say that your mixture of molecules and metaatoms acts as a single effective collective oscillator with much larger coupling strength.
Thank you.
Denis, I actually have a follow-up question to Sergey's one here. Is that right that the mode is actually quite localized at the nanorods?
I don't think so, because the cavities were pretty thick. It was at the resonant energy of the nanorod, there was a few nodes and antinodes. It was not the lowest order Fabry-Perot mode, it was around 10th Fabry-Perot mode. So the field oscillates widely inside the cavity, and the nanorods, of course, they are aligned in a certain horizontal plane of the cavity, yeah. And the results in the extent to which your nanorods experience the cavity field depends on how you place them vertically, because you can place them in the node or in the antinode. And so the results in behavior will depend on where you place your nanorods. Ideally, of course, you want to have a mixture. You want to have a homogeneous mixture. That was not available at the moment. We could not do that. For this test of the hypothesis, we placed nanorods in a specific horizontal plane, and in each case it was a different plane, not perfectly antinodes with a maximal field, but also not the node with zero field, somewhere in between.
Okay, but would it be correct if I say that if I claim that the electric field is maximal at the vicinity of the nanorods?
Not necessarily, because where the electric field is maximal is determined by the cavity thickness and by the energy of your cavity that is realized for that particular thickness. So by placing nanorods, you don't basically change the field profile inside the cavity. Nanorods don't do that. What does change the field profile is the background index of the molecules, because these molecules, they have some background index of 1.3, 1.4, 1.5, and by introducing a medium with some refractive index in the cavity, of course, you change the resonant wavelength of the cavity, right? But nanorods don't do that. Nanorods don't affect the vertical profile of the electric field.
Okay, thank you. Now it's Stepan's turn. Please go.
Yep. Hello, Denis. Thank you very much for a great talk. I was very intrigued by this handiness maintaining cavity, and I have a small question. I can't help but notice that the elementary part of the cavity that you showed for maintaining to make the cavity, basically not just single mirror, to maintain, here for example, is different from what you present when you do the point dipole.
Let's see. So I have the bottom mirror is first and third quadrants. Here, the illustration is different, but let's see if they are equivalent. Okay, good question, good point. Now I am intrigued. So first quadrants, and it looks west to east.
So they are basically crossed in this picture, but on the picture with the here
90 degrees. Okay, this must be the old illustration. I simply haven't replaced the illustration here. Very good point. Thank you for pointing my attention to that. Yeah, of course it is. It was the same structure when the elliptical holes were aligned, stretched in the same direction.
So
thank you.
it doesn't matter which you use, or
it does a little bit, because the dipole here, it does feel the microscopic structure of the mirror to some extent. But if you rotate your mirror is not isotropic, of course, but if you rotate it 90 degrees, 45 degrees, 30 degrees, it shouldn't matter much, because circularly your right-handed wave is reflected into right-handed in the end of the day. So no matter how you rotate the top mirror or the bottom mirror, the system, the reflected wave should be invariant with respect to this rotation, because the right-hand wave is already rotating, right? So it doesn't matter how the mirror is rotated in its plane, right?
Okay.
In this case, it would have mattered for linear polarization, but because our wave is already circularly polarized, no matter how you rotate the mirror, it shouldn't matter.
And one more question is probably more like technical or experimental. I do not have much experience with it, but you brought up an example of ibuprofen, right? It's like organic molecule, but when you're presenting some chiral structures, they are kind of imprinted inside the cavity, like this, ostriches, kind of, this. So is it possible to basically have some organic molecule being absolutely in the cavity oriented, every molecule oriented and structured like this?
Look, I don't think that it will be possible to orient, to align all the molecules. I think this would be insane. So the reason why we used chiral meta atoms in this demonstration was because of their huge oscillator strength, and because we wanted to achieve as large Rabi splitting as possible. This is why we went for meta atoms. But in the end of the day, of course, I'm interested in placing some chiral quantum emitters, such as ibuprofen, pick whichever you like, and observing the effects of coupling for molecular emitters, and not for some postmodernistic meta atoms, which aren't quantum emitters, really.
I mean,
so I don't think it will be possible to arrange them, but it shouldn't matter, because when chiral molecules are not aligned in the same way, they are still chiral. No matter how you align right-handed molecule, it is still a right-handed. This is the key property of chirality. No matter how you rotate your object, it preserves its handedness. And so right-handed ibuprofen remains right-handed no matter how you rotate it, right?
I agree completely, yes. I mean, is it important for the experiments that you showing here, in simulation? I mean, the spacing between the molecules, which is pretty kind of symmetric and pretty same space.
Okay, I now see your points. In this experiment, we were not really aiming for this alignment, but this alignment was the result was the byproduct of the fabrication method, because that was done using whole mask lithography. And in whole mask lithography, every particles become aligned and looking in the same way. But we don't really need that per se. We don't need that alignment. Okay, so we don't care if our molecules will not be light. This will be even much better if they are not. So I don't worry about that personally at all. And the distance between them, it is completely fine if they are closely packed. This is even better for the results in Rabi splitting on the coupling strap.
Thank you for answering.
Any more questions from the audience? Okay, if not, I have a quick follow-up to the chiral cavity. I just wonder, from experimental point of view, what kind of Q factor we can expect from this system. From the experimental point of view, how huge, right?
So theoretically, it is huge. You see, this is the range of 3 nanometers, and the central peak is just a teeny tiny fraction, so the Q is on the order of thousands. But experimentally, of course, so the property of these mirrors, the very high Q factor in this cavity relies on higher reflection, right?
Ah, okay, that's the
high reflection.
single mirror, right?
Yeah,
Okay.
but as long as you have some disorder, some imperfections in a single mirror,
Mhm.
this reflection will drop slightly to 0.9, 0.85, I don't know. And at that point, the Q factor, of course, will reduce. And that is, we still have to see how good these mirrors can be done in an experiment with lithography.
So once again, this is experimental work or theory?
No. This is theoretical.
No, I mean
But
the Canadian group that you
Canadian is experimental. Canadian is experimental.
All right, and they just measured a single mirror, right?
Yes.
Okay, and what's the size of the mirror roughly?
So it was, I can tell you that it was suspended in air. They used HBN flake. It was suspended in air, and they measured in the visible range. And in order to measure all these Jones coefficients, I don't remember from the top of my head, but I would say at least 10 microns you need to be able to measure, right? Because you need to place your laser spot on the mirror without any diffraction. And I guess you don't want to focus your spot very tightly, because then you distort the polarization. So I guess at least on the order of 10 microns.
But how big should be these defects on the mirror? I thought the nanometer scale.
The holes.
Holes, right?
Oh yeah, the holes 200 nanometers, couple hundred nanometers, the characteristic size. And the unit cell is just around the target wavelength, just below the target wavelength, in order to avoid any diffraction.
Okay.
So that the entire thing acts as a metasurface and not as a diffraction, right?
Okay. All right, thanks. And one more question. Actually, it goes to the very beginning of your talk, to the ultrastrong coupling. As far as I understand, at the very high G, the coupling strengths, this nonlinear term in the Hamiltonian, if you go back to Hamiltonian, yeah, here this nonlinear term become dominating part in the Hamiltonian.
Yes.
And I would naively expect that the eigenstates of the system becomes squeezed to some extent. So, can you comment on that?
Yes, I cannot say if they are really squeezed in the quantum mechanical sense, but I can tell you that the eigenstates of this Hamiltonian in the limit of high G. So as we go to the polaritonic stage, when G is about 5–10%, right, we know that the eigenstates become hybrid, 50% light, 50% matter.
Right.
So it turns out that as we increase G, beyond that, the eigenstates decouple. One of the eigenstate becomes again purely photonic, and the other eigenstate becomes purely material-like. This is what Simone de Liberato in his 2014 PRL called extreme decoupling of light and matter in ultrastrong coupling. Quite counterintuitively, although the Rabi split in between the two states becomes super high, but because of the screen, which essentially acts as screening term, it does the screening. The eigenfunctions, the eigenstates again become purely photonic and purely excitonic or purely material in a system with super high coupling strength. So they recover the bare nature.
Okay.
But unfortunately, I cannot tell you anything about the squeeze states. Well, they will be, for example, the two excited states, the upper polariton and the low polariton will be, let's say, 90% photon plus 10% exciton, 90% exciton plus 10% photon. I'm not sure if you can call that squeezed, because squeezing has something to do with the.
I just thought that you can end up with the Hamiltonian that would look like kernel linearity, something like that.
Non-linearity. Well, you see, it is non-linear in terms of A's, but it is already non-linear here because it is quadratic. Quadratic in A's, it is quadratic in B's. It is quadratic to begin with. Non-linearity, if you mean non-linearity in the sense of response to external field, this is a completely different story. This is a completely separate story. But it is non-linear in terms of A's, in terms of B's, in terms of G as well. yeah, it is nonlinear in this from this perspective.
Mhm. Okay, thank you very much. Thanks again for the very nice talk. Yeah,
Thank you, everyone,
let's
for
thank
your
that
attention.
speaker again.
Thank
Thanks.
you very much for coming, Denis.
Cool.
Very good to see you.
Very, very nice to see you all and talk in this seminar. Thank
Yeah,
you,
thanks.
everyone.
Let's be in touch. Thank you.
Yeah,
Bye.
yeah. Bye-bye. Have a nice day, everyone.